So, hello everybody, I am Claire Lallemand and I'm from Cerege in Aix-en-Provence. And today I'm going to present a part of my PhD work about the dissolution of rare earth elements from bauxite residue. So we all know that there is a high increase of the mineral resource consumption these last few years. And it could be explained by the new technologies for the energy transition, but also because of the digital explosions. And among all of these mineral resources, there is a particular one that is the rare earth elements. These elements are very unique because of their specific physical and chemical properties, but they are also very critical, depending on the European Commission, because of their high economic importance and their high supply risk. So because of the increase of the consumption, we must produce more and more to meet the demand. But the mineral and natural deposits are depleting, and the mining activity is very polluting. So in this work, we propose to use another source for the rare earth element, that is a secondary resource, bauxite residue. It is a residue generated from the alumina industry, and it is very produced worldwide. And in this study, we focused on a residue produced in the south of France, in Gardanne. In this plant, Guinean bauxite is used to produce alumina with the Bayer process, and the residue is stored in lagoon next to the plant. But the issue is that this residue is very alkaline. It contains hazardous chemical elements, but the interesting thing is that there is a high content of rare earth elements. So there are some processes to recover the rare earth element from this residue, but they are based on a total dissolution of the residue using strong mineral acids. So this process is not selective. So we propose to use an innovative process on the selective dissolution of the rare earth elements in order to reduce the purification steps. And we will try to use the ligand-promoted dissolution at ambient temperature. So the main objective is to develop an environmentally friendly and selective dissolution process for the rare earth element recovery from bauxite residue. And to do this, we will have to characterize the bauxite residue, and especially the chemical form of these elements in the residue. Then to optimize the dissolution process, so the selectivity and the efficiency. And finally, we tried to understand the chemical mechanisms that occur during the dissolution process. So I'm going to present the multi-scale characterization of the residue that we've done. So first, we realized the chemical composition and the mineralogy of the residue. And it is mainly composed by iron, aluminium, and titanium. And the total content of rare earth elements is around 750 milligrams per kilogram. Then we realized some elemental mapping at the microscopic scale to identify the elemental distribution. And some particles with yttrium, phosphorus, and other rare earth elements were identified. And the interesting thing is that those particles were not associated with major elements. So it's a good thing for us if we want to develop a selective process. Then we characterized these small particles, and we also observe and confirm this collocation with yttrium and phosphorus, and also yttrium and other rare earth elements. And finally, we realized some experiments with X-ray absorption microscopy, which is a technique that gives information about the atomic environment. And for this technique, we choose to do it on yttrium. And the results show that yttrium is in phosphate phases, and it is a mix of amorphous and crystalline phases. So thanks to all of these observations, we conclude that yttrium and heavy rare earth elements were identified as phosphate form in the bauxite residue. But work is still in progress for other rare earth elements, the light one. Then we realized some dissolution experiment with some organic molecules. And these molecules were chosen because they are present in soils, because they could be produced by plant, fungi, or bacteria, because they have a high affinity for these elements, and because they can do the ligand-promoted dissolution, which means that they can solubilize these elements by forming soluble complex. So here is one of the results that we've got. So the first observation that we can make is that there is a difference between the dissolution of the light rare earth elements on the left and the heavy rare earth elements on the right. So the light ones are better dissolved. And this could be explained by the chemical form, so the speciation that we just done in the characterization. So yes, heavy rare earth elements are in phosphate forms, and these forms are really hard to dissolve because they are very stable. So it is that we see with our results. Then we can see that this dissolution is quite selective because we have a low dissolution rate for titanium and iron. And the last observation we've made is that there is no dissolution with oxalic acid and pyrophosphate because there is a precipitation of the insoluble complex that is formed at this pH. Then we were interested in changing the pH to see what happens if there is a better dissolution or maybe a higher selectivity. And so this is the results for the citric acid. And we can see that when the pH increases, there is a steady dissolution until pH 4, which is very interesting because it means that this dissolution is efficient at acidic pH, but also at mild pH. So it is environmentally more friendly. And so we confirm that we have ligand-promoted dissolution at mild pH. And finally, here is an illustration that summarizes the dissolution mechanisms that occur during the dissolution. So I'm not going to go into the details, but we can see that there is two main ways to dissolve the rare earth elements. The first one is based on the solubility product of the rich phases of rare earth elements. And the other one is based on the absorption and desorption. So to conclude, we realized a good characterization of the heavy rare earth elements. We showed that it is in phosphate phases, but the work is still in progress for the light ones. There is a PhD student who is working on it. And he is also working on the speciation depending on the origin of the residue, which can change the mineralogy or other chemical properties. And we successfully made a link between the characterization and the ligand-promoted dissolution because the results of the dissolution showed us that the light ones were higher dissolved than the heavy rare earth elements because of this form in the residue. So it is very important to finally characterize all of the rare earth elements. And we tried to optimize the results by using physical activation like microwaves or ultrasound. And for now, we see a potential for the use of microwaves, but it still needs to be reckoned. And for the perspective and for the future, new molecules are expected to be tested. For example, we know that some bacteria can produce higher selective molecules with a high affinity for the rare earth elements, like lantanophore and lantmodulin. And this could be an inspiration for bio-leaching or bio-sourced leaching. So thank you for your attention, and if you have any question, please do not hesitate.